This is Chapter 9, Geologic Time, Lecture 1. And in this chapter, we'll look at how we use geologic principles to reconstruct Earth history. We will have an introduction to fossils, investigate how they're preserved, and look at them in terms of past life on Earth. We will investigate how the geologic time scale developed, and we will look at the length of geologic time and kind of the main chapters in Earth history. So we'll start out with this image of Siccar Point in Scotland. This is an example of an unconformity, and an unconformity represents missing time. This was made famous, I guess, by James Hutton, who realized that the rock layers at Siccar Point required that Earth had some kind of long history. We have these vertical gray layers of sandstone and shale. They're dipping this way. Over top are these reddish layers in this direction. And the contact between these layers is an unconformity. So what happened here is this rock unit eroded. There used to be more of it. And the reddish layers of sandstone and conglomerate as well were deposited on top. And the contact between those rocks, or the unconformity, suggests that there are two different geologic histories. And James Hutton used modern processes to interpret events that happened in Earth's past, and we call that uniformitarianism. All right, we'll look at the layers in these two photographs. What's different, and what do you think happened when you look at these things? Okay, so just starting out with observations. These are pretty flat. We have flat and more gray-green rocks in the left photo. And we have folded and redder rocks in the right photo. You can trace that here, or flat as such. So most sediment would be initially deposited in horizontal layers. But if the layers aren't horizontal, that means something has happened, such as deformation. Okay. So there's a few guiding principles in geology. One thing is that younger rocks units are deposited on older rock units. So here we have a block diagram with tan sediment deposited over older rock. And then later these red layers are deposited over the tan rocks. And then even later we have our youngest layer deposited on top of that. Pretty simple, right? So if we apply that concept to these rocks, which would be the oldest rocks and which would be the youngest? Well, the lowest rock layers are the oldest. They were deposited first. And the highest rock layers are the youngest layers in a sequence. Well, in that rock sequence. But there's something else that happened. With the development of this river, we have new river deposits that the river carries and deposits here on a kind of a point bar right there. They're not part of the layered rock sequence. They're the absolute youngest sediments. Maybe they're not even lithified yet. Okay, so we can also question what's youngest in the tilted rock layers below and what's oldest. Well, this would be your upper layers, and these are the youngest. And then these are the oldest over here. So from oldest to youngest, it would go in that direction. Something happened that tilted these rocks. Another principle is that younger sediments or rocks can contain pieces of older rocks. So we can look at this rock and determine which part is older. So we have a tan rock matrix here, fine grained sediment. It contains dark colored pieces of volcanic rocks. So in this case, the volcanic rock is older than the tan matrix. And in this photograph, we have granite, a light colored granite containing fragments of dark colored igneous rocks. So those actually got included in the magma that solidified, and it's older than the later magma that solidified into the granite we see now. Okay, another principle is that a younger rock or feature can cross-cut an older rock or feature. So we'll see which feature is younger in each of these images. You're looking at a section of limestone here, and within that limestone are fractures, vertical fractures. So the fractures are the younger feature. The limestone is older than that. Here we have light-colored dikes of granite cross-cutting darker igneous rocks. So the granite, the lighter color material, is actually younger than the dark-colored igneous rocks. It seems simple, but this is when we're only looking at about 2 things in a section of rock. Sometimes we have 12 things going on, and we're always trying to put it in order. Another principle is that younger rocks and features can cause changes along contacts with older rocks. So what we have here, we have heat and fluids from a magma that solidified, affecting an older conglomerate. It forms a baked zone along this dike. So it caused changes along the contacts there. Same thing with this one. A basaltic lava flow baked and retted an older underlying section of rocks. So we can put that in order. Remember, a sill is a horizontal igneous feature. It can bake rocks below and above. Okay, just looking generically, we'll say how a typical landscape forms in terms of geology. Let's say we have pre-existing rock. There has to be something there first. Sediment is deposited on the rock with an environmental change. The environment changes further, and we have new layers deposited on top of that. But perhaps for some reason deposition stops. There's no longer a source of sediment coming in there. After that, we'll see primarily erosion, perhaps by rivers, streams, glaciers, etc. In this case, you get a nice little canyon that starts to form, like the Grand Canyon, formed by river erosion. And that river cuts downward. It carves a deeper, wider canyon. So with that example, we can look at this photograph and consider the sequence of events that likely occurred to get us to this point. And the idea is that the lowest rock layers are the oldest. They're exposed in the bottom of the canyon. They were deposited first. We have middle layers deposited next. And then we have the highest layers in the sequence being the youngest layers on the horizon. All the layers that were deposited and became hard rock were kind of continuous across this area prior to the erosion of the canyon that we see today. Also, it's nearly impossible to see without pointing it out here. We have these igneous intrusions, laccolithic intrusions, in the Henry Mountains baked and domed the layers as well, off in the distance. After that, we had a lot of erosion to form that canyon, and then deposition of river sediments being the most recent event. But a river really cut through and formed this canyon. So that's kind of a generic explanation of how a canyon could form. All right, so how do we determine the ages of landscapes? We have a block diagram here with tilted layers and soil deposited above. The landscape surface is younger than the rocks on which it is deposited. So the landscape itself is younger than the tilted layers. We have a lava flow on top of sediment, and that surface is older, actually, than the rocks deposited on top. The lava flow is younger. There's some other indications of landscape age. All right, and that is seen in this river system with a terrace. This is the terrace, the tall part. Most river terraces formed before erosion down to the present level. But a river runs through this area and further cuts through the sediment that is there. Sometimes we have to use features to infer ages, such as an older river terrace forming before the river eroded down to the present level. We have this landscape with well-developed soil, nicely eroded, fine-grained, fair amount of organic material. That indicates that the area is a bit older than another area with little to no soil and mostly rock. This soil is actually developed on top of a terrace. Let's say perhaps this is older than this part. Okay, so I talked about unconformity in the first couple slides. What does that represent? Well, generically it represents intervals of time missing where there's no deposition from a rock sequence. Something happened. It's the absence of something. In this block diagram, we're seeing gray limestone deposited in a shallow sea. Perhaps the sea withdraws, and later these limestone beds are folded and beveled by erosion later. And then a new layer can be deposited on top. We'd say this is our unconformity, because this is like sediment deposited on top of bedrock. And because these rocks are at an angle to the sediment deposited on top, we call that an angular unconformity, because they're at different angles to one another. Another canyon here. So we have this marked up. Okay, so you have tilted layers that exist below an unconformity, and then horizontal layers above an unconformity. So it's kind of hard to see in this image, but that would be our angular unconformity if we zoom in, because we have the rocks at different angles to one another and then missing time between. There's something else called a nonconformity. And how does that form? So we have a non-layered rock uplifted and eroded. And then we have erosion and the surface buried by sediment. That's called a nonconformity. There's no layers to reference, but we do have missing time in terms of erosion. In my opinion, that's a little more subtle than, say, your angular unconformity. So we have a Precambrian granite in this image. And then an erosion surface being our nonconformity, and then Paleozoic sandstone deposited at the same angle above. All right. So how does a disconformity form? You just have to write these down. There's so many differences, and yet the words are very similar. Okay. So we have, again, deposition of horizontal layers of limestone in a shallow sea. And if the lower rock layers are not tilted before deposition above the unconformity, then the contact is a disconformity. And you have weathering eroding the surface there. When the rock is exposed at the surface, we have that. And then sedimentation resumes, in this case, a simple return of the sea. So these rocks still at the same angle to one another, but very different for a minute. We got just a weathering surface, right? But then we got kind of the same types of rocks forming on top. You have to really look hard for this, or you'll miss it, because we don't have two different types of rocks like we saw with the nonconformity. We have limestone and then erosion, and then limestone deposited again on top of that erosion surface. Look closely and you'll see it. Okay, so there's two disconformities in this photograph. I think they're pretty easy to see. You have older limestone, and then there would be erosion, and then more similar rocks deposited on top, and then erosion, and then younger limestone on top of that. So that's disconformity 1 and disconformity 2. Okay, we'll close out this lecture with brief information on radioactive decay, because that's how we date a lot of these rocks. Okay, this can be confusing for a lot of people, but let's just say I have a generic example of 1,000 atoms that are of one type of element. Start out with 1,000 atoms. We call those parent atoms. Over time, they will decay. We call that radioactive decay. And the time that it takes half of the parent atoms to decay into what we call daughter atoms, now showing up in purple, that's its half-life. So that's the first half-life. After a second half-life, we have only 1/4 of the parent atoms remaining, because yet again, we have half of the remaining parent atoms decaying to daughter atoms, and that keeps going. So again, I'll show you this in chart form. For 1,000 atoms, before any radioactive decay occurs, you start with 1,000 parent atoms. 0 daughter atoms. After one half-life occurs, and half-life is different for every element, we're just being generic here, you only have 500 parent atoms remaining. And then you also now have 500 daughter atoms. Going to the second half-life, 2 half-lives, we take that 500 parent atoms and divide it by 2. We only have 250 parent atoms, and we're adding 250 daughter atoms. So 500 plus 250, and so on. All right. So we have these common radioactive decay series that help us date different types of rocks. We have the potassium argon and then the related argon series, and that's used to date volcanic rocks, cooling really of deep rocks from within the earth. We also have rubidium, which decays into strontium over time. That's used to date old granites and metamorphic rocks and investigate seawater changes over time. Then we have carbon-14. That's for relatively young materials. So that's used to date wood, charcoal, bones, carbon decaying into nitrogen. It's for materials that are only hundreds to thousands of years old. We also have uranium and thorium. That dates old rocks and it investigates sources of magma, like where did that magma originate from. You can use several different methods on a rock to determine when it formed and how fast it cooled. For instance, you could date the uplift time of a pluton. So we have this chart too that shows you temperature and age, millions of years before present. And what we have is a time temperature cooling curve, and how this is just showing how essentially argon age relates to feldspar, the argon age relating to biotite, and the uranium lead age relating to zircon. So you can use several methods for different minerals within a given rock. And we'll stop there for today.